Thank you very much for the invitation to talk at this meeting. So I suppose I'm here to represent maybe what is Thom's most famous work in sort of pure mathematics, perhaps, which is his sort of complete development of Cobordism theory from nothing to proving essentially the best theorem in that subject in one paper. And but I want to sort of explain a revisionist 21st century point of view on how Cobordism might have been developed. Historically, this was not the case, but it might have been, and it's a bit of a different point of view on that subject. So let me start with the classical point of view, and then I'll explain the revisionist point of view. So the classical point of view is to study d-dimensional submanifolds, let's say inside n-dimensional Euclidean space. And of course, if n is very large, then that's studying all d-dimensional submanifolds. And I'm going to draw a sort of schematic picture of Rn and some d-dimensional submanifold. And we're going to ask about submanifolds up to an equivalence relation, which is much coarser than asking are they the same manifold or not, namely Cobordism. So what that means is inside Rn times an interval, if I can find a manifold of dimension 1 higher, which interpolates between these two n's, so this is maybe some m prime, also d-dimensional, and of course that manifold has to be, in the first example you give, the pair of pants, as it's called, then we declare that m and m prime are equivalent. They're cobordant manifolds. When you first see this, most of the examples you can draw, this seems very dull because it seems that all manifolds are cobordant to each other. And that's true. All circles are cobordant to the empty manifold because you can put a disk between a circle to nothing. And so several circles are cobordant to the empty manifold. And the surfaces that you tend to be able to draw are also cobordant to the empty manifold. And so it seems a bit of a vacuous theory, maybe to begin with. Maybe you have to look at a very simple example to see that it's not vacuous, namely that one point is not cobordant to the empty manifold. Because we know what all the one manifolds are. They're all circles at intervals, and a circle has no boundary points, but an interval has 2 boundary points. So 1 point can never be the boundary of a one-dimensional manifold. I mean, that's not the only example of non-triviality, of course, of Cobordism theory. But Thom's analysis of this is to show that it's classifying manifolds up to this equivalence relation is exactly a question in homotopy theory. And at the point where he made that discovery, homotopy theory was well enough developed that it was a question in homotopy theory that you could answer. And he did. And let me first say something about his translation of this. So it uses what these days is called the Thom space. And that's the following. Let me write some notation and then I'll say what it means in concrete terms. We fix some very large capital N, and we look at the space of d minus n dimensional vector spaces in R to the capital N, and we look at the universal bundle over that and take its so-called Thom space. And let me just write out what that means. That's the space of pairs of a d minus n dimensional vector space inside R to the capital N, and a vector in that vector space. And this is what makes it the Thom space and not just a vector bundle, and a point at infinity. And the topology is such that infinity is indeed infinitely far away. So when the length of the vector little v becomes very large, that point gets near to infinity.
What does gamma stand for?
Gamma stands for this vector bundle. I always call it gamma, whatever vector bundle it is. So if we ignore the point at infinity, then this is a perfectly pleasant, smooth manifold. And it contains inside it a perfectly pleasant, smooth submanifold, which is all the vectors of length 0. 0 is a vector in any vector space, and that's contained inside it. And it's contained inside it. If you want, you can go and calculate the dimension of all the Grassmannians, and you can calculate the dimension of this and so on. But much easier is to calculate the codimension of this inside there, because it's exactly the dimension of this bundle, which is by definition d minus n. So this has codimension d minus n. And then the construction goes as follows. If I have some function, some continuous map from the little n-dimensional sphere to this Thom space, I can make the following sequence of manipulations to it. Firstly, so this is just meant to be continuous to begin with, continuous function.
Sorry, we confused on the left. D is smaller than n, and now d is larger than n.
There were, yes, very good. Sounds better, yes. N minus d. Thank you. So apart from this point at infinity, as I said, this is a perfectly reasonable smooth manifold. We can take this continuous function and we can mollify it a little bit to be a smooth function. That's a free thing to do, essentially. We just smooth it locally. And even better than that, Thom proves that one can deform it a little bit more so that it's transverse to this submanifold, meaning it intersects it in the cleanest possible way that you can imagine. So Thom says, so deform to be, well, firstly smooth and transverse to the submanifold. And then once you've done that, you can take the preimage of that submanifold. And the point of transversality is that that will be a submanifold of the sphere. In fact, it will be a submanifold of the sphere minus the point at infinity of the sphere, because this was well away from the point at infinity of the Thom space. And it will be a submanifold of codimension n minus d. In other words, it will be a d-dimensional submanifold. And this, of course, involved many choices. I started with some continuous map. I had to perturb it to be smooth, firstly, and then I had to perturb it further to be transverse. And so the manifold you get isn't canonically associated with the function f, but it is canonically associated to it up to this equivalence relation. Because if I choose different ways of deforming it, the deformation will give me a Cobordism between the two choices. And with a little bit of work, what that tells you is the following. Submanifolds of Rn up to the relation of Cobordism are in one-to-one correspondence with continuous maps from the n sphere to the Thom space up to homotopy. As long as this auxiliary capital N is as big as you like. So this is the translation of a question in geometric topology to a question in homotopy theory, and one can then go on to answer that question in homotopy theory, namely calculate what are these homotopy groups. But that's not the part of the story that I'm interested in today. What I'm interested in today is this correspondence and generalizations of this correspondence. So as I said, that's the classical story. So here is a different story, which will become related to it in a few minutes' time, which is I want to define a space of manifolds. It's called psi d of Rn, and it's the space of all d-dimensional submanifolds of Rn. And when I say all, I really mean all. I don't mean compact submanifolds. I just mean all subsets of Rn that happen to be d-dimensional submanifolds. So it's the space of subsets of Rn such that M is a smooth d-dimensional submanifold.
But closed?
No,
Closed? No.
nothing. One small adjective, which I will say now, which is closed as a topological subspace. But not closed as a manifold. So, I mean, I will draw this picture.
But I mean closed as a topological space.
Yes, yes. So I don't want to allow some sort of accumulation and sort of weird things like that. But I do allow the manifold to be non-compact and to go to infinity and to have many components and to have all sorts of behaviors like that.
What about boundaries?
It can't have boundary, so it's d-dimensional. Maybe I should say without boundary, just to...
You said without boundary.
Yes, yes. So like the picture. So this is a set, and with a certain amount of pain, one can put a topology on this set to make it into a topological space. I will give you an impressionistic, this has a topology, where, what does it mean to be near this manifold? It means that on some very large compact subset of the Euclidean space, you look like a small deformation of the manifold. Okay? But crucially, outside of a compact subset, you can look like whatever you want. Okay?
That the extra component can appear.
Exactly. Because of this property that outside of a compact subset, you can look like whatever you want, the following is a continuous path. Take this and drag it that way, exponentially fast, and at time 1, make it vanish. On any compact region, that path is eventually constant. So that's a continuous path in this topology. So pieces of the manifold can come and go, and not just whole components, of course, but the topology of the pieces can come and go as well. So this space and its topology were developed in a paper of Zongalatius and myself a while ago. Okay.
So this is not compact open topology.
I mean, it's not a space of maps.
Yeah, that is.
There's something, it has a spirit, of course, of something in compact open flavor. It's not a standard construction. So here the manifolds were allowed to be non-compact and sort of encouraged to be non-compact in all possible directions, but you can put constraints that make them be non-compact in fewer directions. So I think I want to call this psi d nk. And whenever I write the symbol, you should tell yourself that means d manifolds in Rn, which are allowed to be non-compact in k directions. So strictly speaking, what is it? It's points in here where m happens to be inside Rk times minus 1, 1 to the n minus k. So in the last n minus k directions, they have to be bounded, but in the first k directions, they don't. So if this is Rk, and this is the remaining directions, you should think of there as being stops in that direction, and then apart from that, the manifold can be whatever you like. Okay. So I want to use these spaces to give another point of view on Thom's relation between Cobordism theory and homotopy theory. Clearly they have something to do with d-dimensional submanifolds of Rn. But as we've seen, they have something to do with non-compact d-dimensional submanifolds of Rn, whereas Thom's theory is about compact d-dimensional submanifolds of Rn. The first point I want to make about these constrained spaces of manifolds is that we can, of course, relax the constraint. If I have a manifold that's non-compact in k directions and compact in n minus k directions, then of course it also happens to be non-compact in k plus 1 directions. It just happens to not use the k plus first direction. So I can include this space into psi d n k plus 1. But if I do that, that map is homotopic to a constant map. Because if I take this picture and I now remove the stops, I can just push everything upwards. And that gives a canonical path to the empty manifold. So that's a null homotopic map. But I could also push everything downwards. And that gives a path to the empty manifold. And in homotopy theory, if something's trivial, then it's trivial. But if something's trivial for two reasons, then it's not trivial anymore. And this is exactly that situation. This inclusion of the manifolds non-compact in k directions to manifolds non-compact in k plus 1 directions is trivial for two reasons. And that's information that you can record. So relaxing non-compactness another way of saying what I said is that if I'm allowed now to be non-compact in the next direction, I can get a loop of manifolds by pushing it up and pushing it down. That gives a loop starting and ending at the empty manifold. So I get a map to the loop space based at the empty manifold of d manifolds in Rn, non-compact in k plus 1 directions, and this is given by a very pretty formula. If I have a manifold and I have a real number, I can translate that manifold by t in the, I guess it's the k plus first coordinate direction. And that gives me a loop that starts, t here you should think of as being in the real numbers, of course. It gives me a loop that starts and ends at the empty manifold. So, theorem is that this map is a homotopy equivalent as long as k is not 0. So in other words, if you're new to this sort of business, you're tempted to think something like, well, clearly it's injective. Because if I have such a manifold and I have such a loop and I evaluate it at time 0, then I get the manifold back, and that's somehow something. But being injective and so on, this has nothing to do with homotopy theory. That's not a meaningful concept. I mean, any map you can change so that it looks injective. That's not a useful thing to know. So the content here is that somehow, if I have a loop of manifolds non-compact in k plus 1 directions, I can integrate it to a single manifold non-compact in k directions. And so I know two...
So, I'm sorry to interrupt you.
Yes.
But your notation, so omega loop space at the empty manifold.
Yes. So I should have said the empty manifold is a manifold.
Also, it has no dimension, but you are going to...
It has every dimension. It doesn't have no dimension. It has every dimension.
Yeah, okay, same thing.
Yes.
I don't understand. How is this map a loop? Because at t equals 0, it's just m.
T here runs over the real numbers, not from 0 to 1. And at minus infinity, it converges to the empty manifold, and at plus infinity, it converges to the empty manifold. Yes. So I know two kinds of proof of this theorem. There's a sort of highbrow proof, which is that the first thing I define, psi d of Rn, I didn't really use that Rn is Rn. I could have taken psi d of any n-dimensional manifold. And in fact, psi d of blank is a sheaf in a variable blank. And it's not only a sheaf, it turns out to be what's known as a microflexible sheaf in the sense of Gromov, which means that it satisfies the H principle on open manifolds. And saying k is greater than 0 is exactly saying that this domain is open, because you have a non-compact direction. So one proof is that this is a microflexible sheaf, and then the H principle of Gromov for microflexible sheaves on open manifolds gives exactly this, if you think about it. But there's also a manual proof, which is a sort of principle that's quite useful to know, which is the following. In topology or homotopy theory, if you're trying to show that some space X is the loop space of some space Y, then X had better have some kind of composition law on it. Because loops you can compose, they have a composition law. And if you can't think of a composition law on X, then you're probably not going to be able to show its loops on something else. And if it has a composition law, X, and you want to show it's the loop space of Y, there's two things you can try to do, or there's two things you simultaneously have to do. Firstly, you should show that with respect to that composition law, it has inverses. Because loop spaces have that property, so it had better be true here as well. And then you should try to check that, in fact, the D loop of this space is Y. So if you have a space with the composition law, you can take its so-called classifying space. And saying X's loops on Y is completely equivalent to saying Y is the D loop of X. But they're quite different propositions to prove. So that turned out to be very successful here. So there's a sort of manual proof by de-looping. And once one understands that manual proof, it turns out you can use the exact same idea to give a new proof of the H principle for microflexible sheaves in general, not just for this one. I won't tell you how either of those proofs actually go, but so this is a crucial stage in the theory, and is quite enlightening for other reasons. Of course, once one knows this theorem, one can iterate it. The corollary is that the space of manifolds in Rn non-compact in one direction, right? If I need k to be strictly greater than 0, the smallest thing it can be is 1, is equivalent to the n-1 fold loop space of what you might call psi d nn, which if you think about my definition, is exactly psi d of Rn. It's manifolds non-compact in all directions. So let me write it that way. Okay, so these are quite fun manipulations with spaces defined in a kind of elementary way, except I didn't tell you what the topology is, but it is sort of elementary, and manipulations between them. But what does it have to do with Thom's theory? So let's think about manifolds non-compact in one direction. And okay, I've always enjoyed my manifolds as being one-dimensional, but let me draw something more exciting. Draw a two-dimensional manifold. And of course, I've drawn ends here, but there aren't really ends. It goes off to infinity. So this is a point in psi d n1. And I want to convince you of the following correspondence. I want to convince you that the set of path components of this space is in correspondence with d minus 1 manifolds inside n minus 1 up to Cobordism. So I've done a sneaky change of indexing to you, but that's the only violence I've done. Okay, this is still manifolds inside Euclidean space up to Cobordism in exactly the same sense I wrote before, except that now these are n minus 1s and these are d minus 1 manifolds. And I want to convince you that this is. Yes, very good. Yes, yes, yes. So if I want to convince you that these are in correspondence to each other, I should describe for you some map to begin with. And the map is given as follows. If I have such a manifold, I can look at projection to the r coordinate, and that function has some non-critical points. It has some regular points. So pick one, for example, here. And if you pick a regular point, you get, as its preimage, exactly a d minus 1 dimensional manifold, compact, in Rn minus 1, namely that slice. So that's what I want this function to be. Intersect t times Rn minus 1 for t regular. So there's two things I have to convince. So I want to convince you that this is a reasonable function, firstly. Well, I picked some regular value, and I could have picked another one. But if I pick another one,
you can have different regular value for different m's, right?
yes, I don't know what t is. So the function is very poorly defined to begin with. For an m, I pick a regular value and take the intersection.
You are picking a value, so
yes.
t depends upon m.
Yes. It doesn't just depend on it. T is not a function of m because there are loads of regular values. But I just pick one. And if I pick another one, then, well, visibly, the region in between is a cobordism between them. And so, because I've divided out by cobordism on this side, the result doesn't actually depend on the t that I choose. So that shows that, in fact, if I don't write pi 0 there is actually a well-defined function. And the second thing is to allow me to put pi 0 here. I need to convince you that this is a locally constant function. But that's just the openness of regularity. If I have a regular value and I perturb the manifold a bit, that value stays regular. And the slice is cobordant. In fact, it's sort of diffeomorphic to the other slice. So those two facts give me a well-defined function in this direction. What about the other direction? Well, I take my d minus 1 dimensional manifold and I cross it with the real numbers. That gives me a non-compact manifold that happens to look like a cylinder. But so what? That has the property that every value is regular, and if I go back, I recover the manifold that I started with. The only thing less, I think, in this sort of sketch proof is that if I start with a manifold and come here and go back, I better convince you that I get the thing that I started with. So what does that recipe do? It takes a picture like this. I make a regular slice. I then replace it with the cylinder on that regular slice. And that doesn't look like the same manifold. But here's where the topology comes into play. That manifold, they do look the same near this slice. And so I can just push away from that slice. And all the rest of the manifold falls off at infinity at both ends. And that gives me a canonical path to a cylinder manifold. That's essentially the proof, I suppose. So this has given a different homotopy theoretic description of the space of cobordisms. It's pi 0 of a certain space. Okay? Now that's much less impressive because any set's pi 0 of some other set, right? So that's, so far we haven't somehow been as impressive as as Thom. But if I combine it with the corollary, this says this is also pi n minus 1 of psi d of Rn. Isomorphic too. So it is actually a homotopy group. But there's something a little funny going on. It's a different homotopy group. It's pi n minus 1 before it was pi n. But that's explained by the fact that it's manifolds inside Rn minus 1 and before it was Rn. So that's actually reasonable. But it's pi n minus 1 of the space of non-compact manifolds, which sounds horrific. Whereas Thom's theorem, it was pi n of the Thom space, which is some finite dimensional reasonable thing that you can think about, which sounds better. And so the final ingredient is to convince you that these are actually very similar. So how does this relate to Thom's theory? I'll say a sentence, then everybody will go, oh, I see. The sentence is the following. What is the space of d-dimensional submanifolds of Rn which happen to be affine manifolds? Or empty. To give an affine manifold, I have to give you a d-plane in Rn, and I have to give you an orthogonal vector to it to tell me where to put it. And I'm allowing the empty manifold, so I'm also allowing the point in infinity. So from that point of view, it's a slightly different Thom space. It's now over the Grassmannian of d-planes in Rn, and it's the sort of orthogonal complement to the tautological bundle. So instead of being a vector in the d-plane, it's a vector orthogonal to the d-plane. But I can think about that as being exactly the space of affine d manifolds in Rn. And when I think about it that way, it's obviously a subspace of all d manifolds in Rn. The ones that happen to be affine. And this is a homotopy equivalence. Essentially, because, let me do a simpler thing first. Let's do linear manifolds, meaning affine manifolds that go through the origin, and manifolds that go through the origin. Well, we can just take a scaling limit. If you have a manifold that goes to the origin, and you scale it outwards, it converges to its tangent space. And you have to do something a little clever with affine manifolds, but essentially that's the idea. So this is by scaling. It's probably difficult to make scaling into an actual proof, but you can make an actual proof. So if you put that all together, I know I have a slightly bad board technique here, but then we've described in different terms the space of Cobordisms as a homotopy group of a Thom space. It's a slightly different Thom space for people who are paying attention. There's not this capital N, which seemed to be kind of unclear what role that was playing in Thom's story, because if you're studying D manifolds in R little n, what has this R to the capital N got to do with anything? And in this picture, it's just not there, so you don't have to explain it. But apart from that, it's exactly the same theorem with all the indices shifted down by 1. And for people, maybe the following sentences are only for people who are interested in geometric topology per se, but I didn't give you full details of the proofs, but I didn't use transversality in the proofs.
You were slicing.
I was slicing. I used, very good. So I used existence of regular values as smooth functions, which is much weaker than transversality. And I use openness of regular values as smooth functions, which is even easier than existence. But I didn't use the fact that you can take something and deform it to be transverse. In particular, this kind of story goes through for other categories of manifolds, not smooth manifolds. Of course, in other categories of manifolds, we also know these days that transversality exists, for example, for topological manifolds. But that's a much harder theorem than transversality for smooth manifolds. Okay. So, yeah.
So for that theorem, the Thom space is compact, right?
Yes.
But on the other side,
it's a nonsense. Yeah.
but what kind of isomorphism?
It's a homotopy equivalence. Homotopy equivalence. Yeah.
I
Yeah.
see. Okay.
Yeah. And it's given by sort of the fact that manifolds are locally linear, which is the defining property in some sense of manifolds. So, right. So this is a sort of revisionist way that Cobordism and the relation from Cobordism to homotopy theory could have been invented and wasn't. But this is not a sort of exercise in being ahistorical, because this point of view does something else. Namely, it sort of categorifies Thom's theorem. In the following way. So there is a, when you draw, oh, I've erased it now. When you draw the standard picture of a cobordism, it's fairly clear that if you have a cobordism from A to B and you have a cobordism from B to C, you can glue them together to get a cobordism from A to C, as long as you have some sort of gluing data maybe given to you. And from that point of view, it's fairly clear that the cobordisms form a category. They're the morphisms of a category. So I want to think of the topological category CD of Rn-1, where the objects are D-1 manifolds inside N-1, compact, no boundary, and the morphisms are cobordisms. There's different technical ways of setting this up that I won't bother you with. Maybe if you want concatenation of cobordisms to actually be associative, maybe they ought to have a length, so that when you glue them together, you get something of length t plus t prime, just like Moore loops in algebraic topology. And maybe if you want to be able to glue manifolds and not worry about whether the thing is still smooth, maybe they ought to be collared near, in fact they definitely should be collared near the boundary. But apart from that, this is a sort of honest definition. I said topological category, meaning there's a space of morphisms, which is essentially pictures like this up to the deformations that you think, and the objects maybe also form a space. And if you have a category or a topological category, it was observed, as far as I can reconstruct, I think, on this campus by Grothendieck, that a category is a certain kind of simplicial set, and in particular presents a space or a homotopy type. And a topological category is a certain type of simplicial space and also presents a homotopy type, which is called the classifying space of the category. From the modern point of view on higher categories, this is roughly, or exactly, depending on how you think about it, the same information as taking the groupoidification of this category. It's the same as forcing all morphisms to be invertible up to some sort of coherent homotopies. The sort of groupoid completion of the category. And the theorem of Galatius, Madsen, Tillman, and Weiss identifies what this is. Strictly speaking, they did it with n equals infinity, but I'm going to write down the answer for n a finite number. And it's exactly the space of D manifolds in Rn, non-compact in one direction. And therefore, by what I said before, is equivalent to the n-1 fold loop space of a Thom space of some bundle over a Grassmannian. And this has a tremendous advantage that, of course, everything inside the square brackets are just standard constructions in algebraic topology, and you can try to study what this space is by using standard methods of algebraic topology, in particular not thinking anymore about manifolds. So I want to give you an impression of why this theorem is true, using the ideas that I've sort of developed today. Oh, even I'm not tall enough to reach that. Oh, I am. So I want to try to explain to you a proof of this theorem, which consists of precisely one picture. And of course, the theorem is useful because it identifies the classifying space of the Cobordism category with something else, but I want to view it as the opposite kind of theorem, identifying the space of manifolds non-compact in one direction with something else. So the proof is as follows. Suppose I have a manifold non-compact in one direction. So I have a point, in other words, in psi d n1. If I want to get an object of the Cobordism category, as we've said, I have to pick a regular value. And because there are non-regular values, picking a regular value is not a contractible choice. If I pick this one or I pick that one, I can't interpolate between them through regular values because there's stuff in the middle. So picking one regular value is not a contractible thing to do. But here's a very glib way to say it. Picking a non-empty set of regular values is a contractible thing to do. What do I mean by a non-empty set of regular values? I don't want to say how many, right? A non-empty set of arbitrary size. So what I really mean is a load of regular values, which you should imagine come with masses. And the fact that it's a non-empty set, I'm going to encode by saying that the sum of the masses is 1. Then there has to be at least one of them. And my claim is that given a manifold, a non-compact manifold, the space of such colored data is a contractible choice. Why? Because it is simply a way of writing the following thing. It's the nerve of the totally ordered set of regular values of this function. And because it's totally ordered and infinite, I suppose, that nerve is contractible, because given any finite collection of them, I can always find one more up here somewhere. So the space of the sort of compound thing, which is non-empty sets of regular values with weights. It strikes me that I forgot to say the most important thing about weights. When the weight is 0, you forget the regular value.
But how do you assign the weight?
I mean, you take the space of all choices. The space of all choices of regular value or set of regular values and set of weights. So weights, they should be non-negative, of course. They should add to 1. And when the weight is 0, you're allowed to forget it. If you are used to this thing, you recognize the weights as simply being barycentric coordinates in the simplex. And so you recognize this as literally being very close to the classifying space of a category, which is defined as a simplicial kind of thing. In fact, the only difference, given such a picture, between this data and a, what would it be? A 2-simplex in the realization of the Cobordism category is all this stuff down here and all this stuff up there. The stuff in between, that is exactly a sequence of 3 composable Cobordisms. And again, the topology saves us, because the bit of the manifold below this is no information. I can push it all to the left, and it goes away. And the bit above here is also no information. So let me say the logic again. I look at the space of manifolds non-compact in one direction. I equip them with this extra data in colors, which is a contractible thing to do, and so it doesn't change the homotopy type. And once I've done that, once I know where the walls are, I know where to put it from, and the stuff down here and up there carries no information, and what's left is visibly a point in the classifying space of the Cobordism category, up to small details like making things collared and so on. So that's my sketchy proof of that. Let me say there are two important consequences of this identification of the homotopy type of the Cobordism category. One is to the classification of topological quantum field theories. So a TQFT is a functor from the Cobordism category to some target. And if the target has the property that all its morphisms are invertible, then such a functor extends over the groupoidification of the category, because everything's invertible at the target, so you may as well invert it in the source. And so topological quantum field theories where the target's invertible can be explained in terms of maps from Thom spaces to something. This has been developed by Jacob Lurie to begin with. You can remove the word invertible if you do a lot more work. And it's been done in detail by Chris Schommer-Priest since then. So that's one important consequence of this theorem. Another is that the Cobordism category knows about the space of manifolds of dimension d of every topological type. If you could somehow communicate to somebody what the homotopy type of the Cobordism category itself was as a category, you would in particular be telling them about what the moduli space of manifolds of every given topological type is, which of course you can't do because you can't even classify them up to diffeomorphism or anything like that. But kind of absurdly, you can identify what you get when you glue them all together. You get the classifying space of the Cobordism category, which has a known homotopy type. So if you could somehow argue that the classifying space of the Cobordism category doesn't change when you drastically restrict what kind of manifolds you allow in it. Maybe you only allow objects, imagine the dimension is 2. Maybe you only allow objects that are circles, a single circle, not many circles. And maybe you only allow Cobordisms which are connected. So they're surfaces of some genus. So imagine you knew that that, which is a very different category, nonetheless, when you groupoid complete it, happened to be the same as the full category. Then it turns out you can relate the moduli space of, in this case, surfaces or Riemann surfaces to Thom spaces. And that's indeed true, and that's the Madsen-Weiss theorem that calculates the cohomology of the moduli space of Riemann surfaces in that way. And if you look at it the right way, it turns out not to be about surfaces. It's something that makes sense for manifolds of any even dimension. And so in work with Son Galatius, I use that principle and this fact or theorem that you can reduce the Cobordism category to a much smaller category without changing its classifying space to give a sort of Thom space theoretic description of the homology of modular spaces of manifolds of higher dimensions. So those are two 21st century applications of Thom's work and Thom spaces. Thank you for your attention.
Well, what is the formulation of all other Cobordism theories? Not just you have Cobordism with extra structure.
I mean, if you just mean tangential structure, then all that can go through. You just have to. Yes, I mean, yes. So when you define the space, you just put that kind of structure on the manifold, like orientations or something like that. And then, of course, that changes the linear manifolds, so it changes the Grassmannian. But apart from that, it looks identical.
You have Cobordism for forms. I mean, I give you D manifold with forms.
With like differential form, you mean?
Sorry?
With the like differential forms? I mean, if you want no properties on the form, then yes, you can. I guess you can talk about that.
It is the same theory?
If you want no properties on the form, it's the same theory because you can deform the form to be the zero form. If you want properties, like if you want the form to satisfy a differential equation, then it's probably very different.
So even though this construction is very topological in nature, but suppose we take this Deligne-Mumford moduli space of curves, does this technique also relate with the, and suppose I want to calculate its cohomology, of course it's known, but...
No, it's not known. So maybe the closest thing to that would be that I might like to allow, so in this picture, going to the Deligne-Mumford space means allowing nodal singularities.
Yes, absolutely.
And if you just allow them in all possible ways, then it also fits into this story. You get something more complicated than a Thom space. The Thom space, remember, was showing up as the space of all infinitesimal models of what a manifold can look like in Euclidean space. And it just looks like a plane, maybe it doesn't not going through the origin. If you want to now allow node singularities or so on, that also is encoded by what the local structure is, but it's of course more complicated. So there will be some part that looks like a Grassmannian that corresponds to smooth points, and there'll be some part that looks like something else. So this was worked out by Jascha and Søren Galatius, and the only reference is the Ober-Wolfach report from about 20 years ago.
So it can be done. So there is some...
There's something, it turns out you cannot use that to describe the stable cohomology of ng bar because it doesn't stabilize, is one reason. Yes. Sorry? How do I get it? I don't get it. I insist on it. So I only take systems of weights that sum to 1. I mean, they're really like barycentric coordinates in the simplex, which are by definition sum to 1.
Can I ask one more question? Sorry. If I replace R capital N by some, you mentioned that something.
You can replace it by other manifolds.
Yes.
Yes.
Is there a similar theory?
There's a similar theory. The place where I say loops n plus 1 should then be some sort of compactly supported sections on whatever manifold you have in mind of a certain bundle over that manifold. Which, I mean, yeah, you can try to think about that. So really here, implicitly I sort of use the Euclidean space is framed. Euclidean space has trivial tangent bundle. So I can untwist that bundle and I just write it as a mapping space.
If there are no more questions, we thank the speaker.